All right, next we're going to be looking at power functions, and we're going to be looking at the different graphs that go along with power functions and a couple of properties that also go along with them, and how we're going to be using these power functions in the next couple chapters. So to start out, what is a power function? It is when you are taking some constant times x to the power of a. And so here I have my independent variable of x, and x is being raised to an exponent, is being raised to a power. K is just a non-zero constant, so it can be any number. So an example of a power function then we could say is f of x is equal to 5x to the 7th power. That is a power function. We could say that g of x is equal to 1/3 x to the power of 1/5, and that right there is also a power function. And we're going to focus mostly on today what the graphs of these different power functions look like. Now, if I had you guys in class, what I would have you do is take your graphing calculators and look at the graphs of, as I have them here, 12 different power functions. And as you look at all of these power functions, you'll notice that I just increase the power by 1 every time. So I've got x to the first, x squared, x to the third, x to the fourth, and so on. And if you graph these out on your graphing calculator, this is what the general graph would look like. Now, what I want you to look to see here is, can you see a pattern that's happening? And do you notice something? Hopefully what you are seeing and recognizing is the fact that a lot of these look like parabolas, where we have that U shape of a graph. And if we look at when that's happening, we've got x squared, x to the fourth, x to the sixth, x to the eighth, and x to the 10th, and x to the 12th. Well, I bet that if I were to continue on here, you would be able to sketch a graph of what you thought of x to the 14th would look like, or x to the 16th possibly looks like. And it's going to have the shape of our U that we've seen with the quadratic function. Then when you look at the functions that have a odd power to them, so x to the first, x to the third, the 5th power, the 7th, the 9th, and the 11th, you'll notice here that minus x to the first, which is a linear function, so it's going to be that straight line, the rest of them here have that cubing function look, which is that nice curve that we get going through the first and the third quadrants. And so if I were to ask you to sketch a graph, what does x to the power of 31 look like? I would think that you would be able to say that it's going to have this nice curve like the cubing function versus the parabola that goes along with our quadratic function. So with our power functions, as we start to look at them, two power functions that we'll see every once in a while is x to the power of 0, which this does not quite fit in with all of the patterns that we're going to see here in the next couple minutes. But x to the power of 0, remember that's the same thing as x equals, or 1. So x to the power of 0 is 1. So here you're looking at f of x equals 1. So you have a horizontal line going through the y-intercept at 1. F of x equals x to the first power. That's our linear function. So you have a y-intercept at 0, and you have a slope of 1. And so there's our linear function. Moving on to what happens when you have different exponents, and more so when you're looking at positive even integers for an exponent or a positive odd integer for an exponent. If you have a positive even integer, so x to the second, x to the fourth, x to the sixth, and so on, your graph is going to end up resembling this parabola that we've been working with for our quadratics. Now with this parabola here, this is telling us that we have an even function because it does have y-axis symmetry. And as I start looking at the end behavior, which is going to become very important to us in a little bit here, as x goes to infinity, our value of y is also going towards positive infinity. As x goes towards negative infinity, our value of y is also going towards positive infinity. So that's for a positive even integer for an exponent. If you had an odd integer, so we're looking at x to the third, x to the fifth, x to the seventh, and so on, you're going to get the line that represents the cubing function. And this function here that we're going to be working with is going to be an odd function. And both of these being even and odd, this is before any transformations take place of moving it left, right, up, or down. But it's an odd function, meaning it has rotation symmetry. And if I look at the end behavior, as x approaches infinity, y is also going to approach positive infinity. And as x approaches negative infinity, y is also going to go towards negative infinity. So there's kind of the pattern that is going on when you have even and odd integers for the exponent. Now let's take a look at what happens when you have negative integers for, or negative whole numbers for your power functions as your exponents. So I have x to the first, which this is the same thing as 1 over x. X to the power of negative 2 is 1 over x squared. X to the power of negative 3 is 1 over x to the third, and I continue with this is 1 over x to the fourth, and so on. So now you'll notice that when we were talking about the inverse function, we talked about having these two branches, and we looked at this function here of 1 over x, and we had these what we call branches in the first and the third quadrant. Well, this continues on as I work with negative 3, as I work with negative 5 and negative 7, negative 9, and negative 11. And again, if I were to continue going on to negative 13, you would again see a branch in the first and the third quadrant. When we start looking at a inverse function here, which is being squared, what's happening now is now we are looking at our branches being in the first and second quadrants. And the reason for all of this is because when you take a negative number to a even exponent, you're always going to end up with a positive value. So there's no way that we can end up with any y values that are negative, therefore putting our two branches in the first and the second quadrants here. So another pattern that we're going to be looking for is when you have a power function, when you are taking it to the power that is going to be a negative even integer. So I'm talking about negative 2, negative 4, negative 6, and so on. When you have a negative even integer, this is when we're going to have our two branches that are going to be in the first and second quadrant. So you're taking x to the power of negative 2, x to the power of negative 4, or thinking about it as x over, or 1 over x squared, 1 over x to the fourth. This is what our graph is going to look like. This would be considered an even function since it does have y-axis symmetry. And our end behavior, as x approaches infinity, our value of y is going to go towards 0 since we have these horizontal asymptotes along the x-axis. And as as x approaches negative infinity, your value of y is also going to go towards 0. When you have a negative odd integer, we're going to see those branches going back to the first and the third quadrants, which will give us rotation symmetry. So now we have an odd function. And with an odd function, if I look at its end behavior, as x approaches positive infinity, our value of y is going to approach 0. And as x approaches negative infinity, our value of y is also going to approach 0. So it's because we have that horizontal asymptote along our x-axis there for our end behavior. So this is taking care of our integers. Now we can see what the general graph is going to look like if we had a positive or negative whole number. And now we're going to look at what happens when we start working with some fractions. So I'm going to work with positive fractions to begin with here. And so I have x to the power of 1 over 1, x to the power of 1/2, 1/3, 1/4, and so on. Well, when you're taking powers to the 1/2, the 1/3, the 1/4, what we're doing here is we're working with nth roots. We're talking about taking the square root of x. Here we're taking the cubed root of x. Here I would be taking the fourth root of x. And when we think about that square root function, you should be familiar with the graph here, where we just have this line starting at 0, 0, and then increasing in quadrant 1. And the reason we're only in quadrant 1 is because you cannot take the square root of a negative number, so therefore your domain has to be greater than or equal to 0. Well, this same graph exists for when you're working with 4th roots, 6th roots, 8th roots, 10th roots, and even 12th roots. Because when you're taking a nth root and you're talking about an even nth root, you can only take that of positive numbers. Now, when we start working with cubed roots and something that's of an odd root, now we can actually work with nth roots, or negative numbers, I'm sorry. So when I take the cubed root of -8, I know my answer can be -2. And so we can use those values to help, and now we extend on that graph a little bit, and now it's very similar to that cubing function that we talked about just a little bit ago, but it's kind of turned on its side here a little bit. The fact that I have the function of x to the power of 1 over 1, you'll just notice that even though that's a linear function right here, you still have your end behavior going in the same direction as the rest of them that I have highlighted here in blue. So just to kind of look at the general side of power functions when you have, as I wrote down here, an even fraction, and what I just mean by that is that your denominators of even whole number. And so when we're taking x to the power of 1/2, here's what our graph is going to look like. In an odd function, it's going to look more like this. Now, when we take x to the power of 1/2 or 1/4 or 1/6, this is neither odd nor even the even function, because there is no y-axis symmetry and there's no rotation symmetry. But we can talk about the end behavior, and the end behavior is only going to be for when x approaches positive infinity, since we are starting at 0, 0 for this graph. And the end behavior would say that as x approaches positive infinity, y is also approaching positive infinity. If we look at an odd function here, this one does have, or an odd fraction, this one is an odd function. It does have rotation symmetry to it. And its end behavior as x approaches infinity, y is going to approach infinity. And as x approaches negative infinity, y is going to approach negative infinity. And so now that we've gone through all of these, what we should be able to do is now come up with the sketch of different power functions. And when I say the sketch of it, doesn't need to be perfect, but just recognizing what is the exponent and what is the end behavior going to really look like. So here I have a function of f of x equals 2x to the power of 7. The fact that my exponent here is going to be 7, this is telling me that it's an odd positive integer, and so that my graph needs to resemble that cubing function, which is going to look like this. That 2 is going to help us stretch this vertically, and as far as our transformations go. If I look at the next one here, I have -4x to the power of -6. Well, going back to our transformations, this negative out in front here is going to tell me that I am going to do a reflection over the x-axis, so I'm going to wait to do that. First of all, I'm going to start with my negative exponent that I have here of -6. And if I just drew this out as f of x equals x to the power of -6, I would have my two branches up in the first and the second quadrant. Now, because I am reflecting it over the x-axis, now this graph is going to end up being in the third and the fourth quadrants. And so it's going to be those two blue lines. Just to do one more here, if we take f of x is equal to -0.4 x to the power of 0.5, this negative out in front is going to tell me I'm going to do a reflection over my x-axis once again. So I'm just going to start with looking at what is the function of x to the power of 0.5 look like, which is the same thing as x to the power of 1/2, which means we're working with our square root function. So here's my square root function, and since I'm reflecting it over my x-axis, I'm going to want my graph to look down here in the fourth quadrant. So that is that. We have now covered the section working with power functions, and what I'd like you to do is come into class looking at or sketching out a graph of these three functions, and just sketch out the graph, bring that with you to class so I can see if you've got a good understanding of what's happening and what the graphs look like. And that's it.